Yonder Dynamics is an undergraduate autonomous robotics organization at UC San Diego. At Yonder, our primary objective is to help our members discover a higher potential and to allow them to realize their creativity and drive. This is our very first year competing at the University Rover Challenge, which means this is the very first rover we've ever built. We've learned an incredible amount along the way, and we've built an amazing family. We can't wait to hit the road and show the world what we've created.
The Rover's chassis was water jet cut from 6061 T6 aluminum sheet metal, which was then welded together to house all of the Rover's systems.
In designing our rover, we took into consideration what it would take to drive a 50-kilogram rover up a 45-degree incline. Based on our calculations, we developed a drive system to meet and exceed these expectations. The resulting design, based on our rocker bogie drive system, has 4 contact points of the chassis as opposed to the traditional 2-point system. The final iteration of our rover will have a differential gearbox bridging these 2 rocker components for a greater degree of control and stabilization.
The modular arm also has a telescoping feature which allows for greater reach and range of motion of the feet. In addition to this, our team is prototyping a multitude of interchangeable hand and drill attachments using dragon skin polymer and soft robotics to work cohesively with our rover's autonomous system.
The rover will be powered by a 20 amp hour lithium ion battery, but currently we're prototyping with his 14 amp hour sealed lead acid battery. The power budget has been allotted such that the rover can travel for over 1 kilometer in distance and run for 2 hours in time. The rover will be controlled by a BeagleBone Black and the NVIDIA Tegra TX1. The BeagleBone Black will be used to interface all of the sensors in the motor drivers. The Tegra TX1 will be used to run computer vision algorithms for the rover's sight. For the communication on the rover, we have an omnidirectional 5 dBi gain antenna connected to a Bullet M2. On the ground station, we have a 15 dBi massive antenna connected to another Bullet M2.
For the software team, we're planning on having manual control be a last resort. We're using a combination of ultrasonic sound emitters and a stereo Z camera. For obstacle avoidance, the ultrasonic pinger will be mounted on a servo, which will sweep back and forth and take elevation data for our rover. At the downward angle of this ultrasonic emitter, we're able to tell both elevation and the presence of crevices and drop-offs. In the event that our rover encounters a dead end or difficult scenario that the ultrasonic emitters can't detect, the Z camera will be able to create a terrain map just like the ultrasonic emitters, but with much more resolution. We're able to use the stereo camera to determine the distance away from the rover.
For the science cache task, we will use computer vision software to look for geologic features such as channels, paleocurrents, cross-bedding, and other stratigraphic markers. Once the rover chooses a site based on these criteria, we will deploy a non-invasive soil conductivity payload which will test for soil moisture and temperature at a depth of 10 centimeters. Our drill system incorporates a diamond cutter and auger tip in a combination with the soil coring system, and we also have switchable drill heads to minimize contamination and sample different types of soil. Once we obtain the sample, we will transfer it to the chassis and use our Raman spectrometer to look for evaporitic minerals with a 532 nanometer laser. Our final in situ test is a 3-axis flux gate magnetometer so we can investigate habitability in regards to the magnetic field of Mars.
Our off-rover test will evaluate samples for signs of life. We will test for pH, salinity, and soil texture in addition to our elemental colorimetric tests. In addition to these tests, we have also developed a biosignature wet chemistry lab unit that uses fluorescent probes to test for nucleic acids, amino acids, and hydrocarbons.
In building autonomous rovers and in competing at URC, we hope to be more and to do more for this world.